So our motivating question for this video is, how do we know if or when a geometric series converges? So we saw in the last video that 1 over 2 to the n converges, but how do we know if any geometric series converges? So remember our process. We're going to look at the sequence of partial sums and see if that sequence converges. This is the same as asking, when does the limit as n approaches infinity of s sub n, those are our partial sums, when does that limit exist? Okay, so we're starting with our geometric series, and I want to look at the nth partial sum. So this is s sub n, and it's equal to the sum from I equals 0 to n minus 1 of a times r to the I. Okay, so I'm starting at I equals 0 and going to n minus 1, and we do this so that we are adding the first n terms. Let's make sure that makes sense. So we're doing a plus a times r squared, etc., until we get to a times r to the n minus 1. So a is the first term, a times r is the second term, a times r squared is the third term, and then when we do this, a times r to the n minus 1 will be the nth term. And we want this to be the case since s sub n is the sum of the first n terms. So we're going to look at the sequence of these partial sums and see if it has a limit, see if it converges. So in order to find the limit of these partial sums, we're going to need to rewrite them in something that looks a little bit simpler. So this process takes a little bit of time, but it really does play an important part when we are determining the convergence of geometric series. So try to follow through. I think it's also just a good exercise in the types of work that we do in mathematics behind the scenes. Now remember, the whole goal is to get something that looks a little simpler so that we can take the limit of it. Because right now, with this sum, I don't really know how to take the limit of it. I'm not really sure what's going on. I need something that gives me more information or that looks different so I can determine the limit as n approaches infinity of this value. So first, I'm going to take the second term and on and factor out an r. So these all have an r in them and I'm going to factor it out. And so I'm left with a times a plus r squared, etc., all the way up to a times r to the n minus 2. So I've taken an r out of each of the terms that have one. And so whereas I had r to the n minus 1, now I have r to the n minus 2 since I took out an r from that term. I factored it out. So what we are left with in this portion that we have factored out an r from is s sub n minus 1, the n minus 1 partial sum. This is because it shows the sum of the first n minus 1 terms. Now bear with me, we're just doing this because it gets us something interesting. This is the sort of thing you play around with until you see that it works and that it has a cool result. So now I'm going to add in a times r to the n minus 1 and subtract it off just so I leave the equation the same. Basically, I want to get the first n terms rather than just the first n minus 1 terms. So now I have s sub n, I have the nth partial sum, and I can rewrite it as that. I just have this minus a times r to the n minus 1 left over. Okay, so I have this statement, and I'm going to solve it for s sub n. I'm going to solve it for the nth partial sum. So I've done this cool thing where I've rewritten what we had in terms of itself. So I've written s sub n in terms of itself, just with some other terms, and I'm going to solve for s sub n to get a new thing. So let's distribute the r. I have that the nth partial sum is equal to a plus r times s sub n minus r times a r to the n minus 1. Now when I do this, I'm going to have minus a times r to the n, since we can combine those r's together. And I'm going to collect like terms. I'm going to put all of my s sub n terms on the left-hand side. So I'm getting that s sub n minus r times s sub n is equal to a minus a times r to the n. This is a lot of variables to read out loud, so hopefully you can follow along all right. Now I'm going to factor out the s sub n from the left-hand side. So I have s sub n times 1 minus r, and I'll factor out an a from the right-hand side, just because I can. Now, solving for s sub n, the nth partial sum, I have that it is equal to a times 1 minus r to the n, all over 1 minus r. Now I have a way to look at the nth partial sum that is just in terms of n. So if I tell you that I want the 100th partial sum, you can just plug in 100 for n and tell me what it is. That's pretty cool, and it's going to be really powerful when we're trying to find the limit. Okay, so remember, we know that the infinite series converges if the sequence of partial sums converges. So for the geometric series, we know it converges if the following limit exists. So this is the limit as n approaches infinity of the partial sums, which are equal to the sum from I equals 0 to n minus 1 of a times r to the I. We discussed that earlier. But now we know that this is equal to the limit as n approaches infinity of a times 1 minus r to the n all over 1 minus r. So we have this new limit we can worry about and determine where this limit exists. Specifically, we need to determine what conditions will make the limit exist, and this is going to depend on a couple of cases. But let's try some things to get a sense for what's going on. Looking at this limit, I'm noticing that the a and the 1 minus r don't depend on n, so I can factor them out of the limit. Specifically, the a and the r are fixed based on the problem, based on the specific geometric series we're looking at. So they don't change, but we still have the limit as n approaches infinity of 1 minus r to the n. And this is going to change depending on whatever r is. So for example, as we saw with 1/2 for r, 1/2 to the n goes to 0. But 2 to the n is going to go to infinity as n approaches infinity. So the value for r is going to affect this limit. Now, formally, this would take quite a bit of work to go through all the steps, and you can find that in textbooks or in other videos, but I just want to give you the basic cases here. So the first case is where the absolute value of r is greater than or equal to 1. Remember that r can be negative, so that's why we're using absolute values here. So what's happening is that basically r to the n, that will grow bigger and bigger as n approaches infinity. So as n gets larger, we're taking something bigger than 1 and multiplying it by itself over and over and over again. That's going to get really large. And so the limit with the 1 minus r to the n is going to go to infinity in some way. So the limit of 1 minus r to the n is not going to settle on a specific point. It's just going to continue to grow and grow. There's some nuance here, like if you have a negative r value, the series is oscillating, like some of the partial sums are positive and some are negative, they go back and forth as the powers switch. It's not oscillating back and forth and then settling on a point, it's oscillating back and forth and growing larger and larger. Additionally, if we had r is equal to 1, this is just the sum from n equals 0 to infinity of a, which doesn't converge. It's just the same thing added to itself an infinite number of times. But really what you need to know is that the geometric series diverges when the absolute value of r is greater than or equal to 1. Now for convergence, we're going to look at the absolute value of r is less than 1. So this is anything between -1 and 1. And what's happening here is that basically r to the n goes to 0 as n approaches infinity. In this case, it helps me to think of r as a fraction that's less than 1 or a decimal that's less than 1, and think about what happens to that as we increase the power on it. So as we multiply it by itself over and over and over again, it's getting closer to 0. Knowing this, we can compute the limit of the partial sums. So we have that a over 1 minus r on the outside, and we're taking the limit as n approaches infinity of 1 minus r to the n. This is the thing we found earlier when we were looking at rewriting the partial sums. Then r to the n goes to 0, so I really have a over 1 minus r times 1 minus 0 when we've evaluated the limit. And this just gives me a over 1 minus r. Okay, so let's take a step back and make sure we know what's going on here. When the absolute value of r is less than 1, the sequence of partial sums is converging, and it's converging to a over 1 minus r. Since it is converging to this value, the infinite series is also converging, and it's going to be equal to this value, a over 1 minus r. So we can write this by saying the geometric series converges when the absolute value of r is less than 1, and in this case, the sum from n equals 0 to infinity of a times r to the n, that's our infinite geometric series, is equal to a over 1 minus r. I think that's super cool. So if you have an r value that's between -1 and 1 for your geometric series, I can tell you what the infinite series is equal to by using the formula a over 1 minus r. Pretty cool. So again, there are lots of formalities we could talk about here, but I really just want you to be able to recognize geometric series and know the basics of how they converge. there can be a lot going on when you're thinking about an infinite series and then a sequence of partial sums of that series, and so it's a lot to keep track of, and I think the geometric series is one way to get more used to those ideas and more fluent working with them. Thanks so much for watching, and I will talk to you in the next one.